Hello everyone, in this video we are just going to demonstrate UART serial communication receiving a byte of data in RL78 bar F14 series microcontroller. Let's get started. So I'm just opening the CubeSuite Plus IDE. So now after all the basic necessary configuration that needs to be done for the microcontroller, we just want to configure the UART port of the microcontroller for demonstrating it. So I am moving to the watchdog timer first and I am going to click on unused radio button for disabling the watchdog timer of the microcontroller. And then coming to the serial UART peripheral, just double click on the serial tab right over here, just select or click on this drop down and select UART 0, and here click on the drop box and then select transmit or receive function. And coming to the UART parameters, just click on the tab UART 0 right over here, and you can see the data line settings is set to 8 bits by default. So it is okay. We are just going to transmit and receive a byte of data in our UART communication. And transfer direction settings by default is LSB first, so just leave it as it is, and parity is none. It is okay for me. And the baud rate right over here. So this is the speed at which the UART communication happens. So this is very important. This baud rate needs to be setted each time as per the device that you are communicating. So the opposite device, which is also communicating with the microcontroller, needs to run in the same baud rate of the microcontroller. So you can select varieties of baud rate. Just click on the drop box and you can see there are varieties of baud rate available. Just click on 9600, which is a standard baud rate, and then check this box reception end error if required. So I am leaving it as it is. So that's all about the configurations that needs to be done. And in addition to that, I am just going to utilize the P67 LED in the development board. So in our development board, we just found that there is an LED which is connected to P67 of the microcontroller, that is port 6 7th pin. So I'm just double clicking on this port pin and going to the port 6 tab. I'm just going to configure this P67 pin as output pin by clicking on the out radio button right over here. So that's all about the serial communication configuration as well as the required LED output pin configuration that needs to be done, which is available in our development board. Now I'm just going to click on the generate code button right over here for generating the base drivers required for the project. You can see it is generating and it has been generated. Just click on the plus icon right over here in the code generator, and you can see this is the main file, main.c source file, which has been generated for our project. This is the main function. And in addition to that, we also has got some new files added to our code generator folder. One is the serial.c. rcg serial.c, rcg serial underscore user.c, etc. So these are the files required and generated for UART peripheral of the microcontroller. So in this, what I will do is I'm just going to declare a 8-bit variable called RX data. And now what I will do is I will just extend the scope of this variable to this rcg serial user.c file. So how can we do that? We just want to do that with the help of extend keyword in C language. Extend uint8 underscore t rx data. When you write like this, the same variable which has been declared and defined right over here in the main.c will be extended to the serial user.c file right over here. So it is not a different variable. Instead, this extend keyword in C will extend the scope of this particular variable which has been declared and defined in the main.c file to the serial user.c file right over here. So now we are just going to utilize this 8-bit variable for receiving the data through serial communication. So come down a little bit, you can clearly see there is a function called UART0 interrupt receive. So this is the interrupt function which will be called whenever a byte of data has been received successfully over the serial communication channel of the microcontroller. So UART0 is the serial communication channel configured in our microcontroller, and for that UART0 we have an interrupt service routine function right over here. So this function will be called when a byte of data has been successfully received completely in the serial buffer of the microcontroller. So coming down a little bit, you can clearly see there is a line right over here. Rx data some variable is equal to SDR01L. So this is the serial buffer of the microcontroller which will be holding the received data. So here they are manually moving the value that has been received from serial buffer to a local variable called rx underscore data. You can clearly see this is a 8-bit variable. So what I will do is I will just write a line right over here, rx underscore data, which is a global variable which I have extended the scope from the main function, is equal to this variable. I am saving this. So after successful loading of the serial buffer to this rx data local variable to this function, I will load the value that is available in this rx data variable, local variable, to my global variable, which I will be reading in my main.c file inside the main function. So this rx data right over here will be holding the data received through serial communication. So that is the concept. So now coming to the main function, coming inside the while of 1, I am just going to continuously monitor the rx data variable. Rx data is equal to 1. If it is 1, that is, if the data that has been received in the serial communication is 1, I will just turn on the LED which is connected to P67 pin of the microcontroller in my development board which I am using. So what I will do is P6 is equal to P6 ampersand of negation of 1 left shifted by 7. So this will turn on the LED. So this will turn on the LED, so making the particular pin low will turn on the LED, since the cathode of the LED is connected to the GPIO pin of the microcontroller. So we just found and discussed that earlier in the video while we have been discussing about the schematic diagram of the board. And now another check which I am going to add is, I am just going to add like rx data, if it is holding the value if equal to 2 in ASCII, I will just turn off the LED by making the pin 1. So this is ASCII format number 1 and this is ASCII format number 2. Since UART uses ASCII formatted alphabets and numbers, we are just checking for the ASCII formatted numbers right over here. If it is 1, which is the data received in UART communication, I will be turning on the LED. And if it is 2 in ASCII, which has been received in the UART buffer of the microcontroller, I will just turn off the LED. That's it. That's all about the programming logic that I have built. Now I'm just compiling this code by clicking on this icon right over here, or F7 in my keyboard, shift plus F7 in my keyboard. You can clearly see the build is successful with 0 errors and 0 warnings. Now I'm just going to dump the program to my development board by clicking on the F6 in my keyboard or this icon right over here. So now let us try to understand the schematic diagram that we are going to build with the help of this Renesas RL78 bar F14 series development board and the USB to TTL converter for testing the UART transmission and reception. So you can see this is the development board, and in this development board we just analyzed that the RX pin is connected to CN2 connector 7th pin and TX pin is available in the same connector CN2 5th pin. So we will be utilizing these two pins. So these two are the RX and TX of UART 0 of the microcontroller that we are going to enable. And in addition to that, we are just going to utilize the ground right over here in the CN1 connector. So this is the common ground for the development board as well as the circuit. So this is available in CN1 connector pin number 43. So these three are the connections that we are going to make between development board, this development board and the USB to TTL converter. So you can clearly see the P15 is the TX pin of the microcontroller, that is UART 0 TX pin, and P16 pin of the microcontroller is the UART RX pin. So we will be connecting the TX of the microcontroller to the RX of the TTL converter and RX of the microcontroller to TX of the TTL converter. So this is the USB to TTL converter. So this converter is useful for converting one level of voltage signal into another level, that is from the level of voltage signal from microcontroller level to PC USB level. So we will be utilizing this USB to TTL converter or USB to UART converter for transmitting and receiving data between PC serial terminal software and our microcontroller. So you can use any one of USB to TTL converter. So I will show you while I am connecting what is the type of TTL converter that I am using. And on the screen you can see this is the type of TTL converter that I am going to use in this video. So in this TTL converter I will be connecting the mini USB cable from this TTL converter to the PC USB port, and in the other end of the TTL converter I will be connecting the ground of the TTL converter to the ground of the development board, and TX of the TTL converter will be connected to RX of the microcontroller UART port. So UART 0 RX pin is P16. So I will be connecting the RX pin of the microcontroller to the TX pin of the TTL converter, and RX pin of this converter will be connected to TX pin of the microcontroller UART port. So UART 0 port pin of the microcontroller is available in the CN2 pin number 5, that is P15. So this TX pin of the microcontroller will be connected to RX pin of the TTL converter. So that's all about the circuit that I'm going to make between the development board and the USB to TTL converter for establishing the UART communication between these two, that is between the serial terminal software in the PC and the microcontroller RL78 bar F14. So I hope you understood the circuit connections. So let's see how we can configure this UART further in the microcontroller and how we can transmit some byte of data through the UART serial port of the microcontroller. So you can see this is the USB to TTL converter that I am using for transmitting the data from my microcontroller to the PC serial terminal and from the serial terminal of the PC to the microcontroller serial port. So this TTL converter will help us to convert the high level signal from the PC USB port to the microcontroller level signal. So in this terminals, we are just going to utilize only three terminals. One is the ground pin of this TTL converter, which is connected to the violet jumper wire, will be connected to the ground of the development board. That is the CN1 connector, pin number 43. You can clearly see here 49753. And other than that, the two terminals that we're going to utilize from this TTL converter is RX and TX. So RX is connected to gray wire and TX is connected to brown jumper wire. RX of this TTL converter will be connected to TX of the microcontroller and TX of the TTL converter will be connected to RX of the microcontroller. So this particular RX, which is connected to gray jumper wire, is connected to TX of the microcontroller UART 0 port, that is the P15, and TX of this TTL converter, which is connected to brown jumper wire, is connected to RX of the microcontroller, that is the P16. TX pin of the microcontroller is nothing but P15, which is connected to CN2 pin number 5. So CN2 connector is right over here and pin number 5 is 135. And RX pin of the microcontroller is nothing but P16, which is the CN2 pin number 7. So 1357. So right over here we are utilizing RX and TX. Right over here we are connecting RX and TX of the microcontroller to the TX and RX of the TTL converter right over here. So that's all about the connections. TX of the TTL converter will be connected to RX of the microcontroller and RX of the TTL converter microcontroller will be connected to TX of the TTL converter. And then we are commonly sorting the ground of the TTL converter to the ground of the microcontroller right over here. So now I'm just going to run this program, and as per the expectation of this program, the output is very simple. When we receive the character 1, that is 0x31 in hexadecimal in the UART 0 receiver, we will turn on the LED, and when we receive the character 2, we will turn off the LED. So this is the basic expectation of this program. So let us test whether we are getting proper output for this. I am just going to add this RX data variable to the watch window for monitoring it. Right click, double click on this variable, right click and just click on register to watch 1. You can see the register has been added to the watch window. Right click and hover over notation and select ASCII for viewing the data in ASCII format. Now I am just going to open the doclight. So we already configured two outputs that we are going to send, byte 1 in ASCII and another one is the byte 2. So when I click on this button, I will get 1 transmitted in the UART channel connected to the PC, that is the TTL converter connected to the PC, and when I click on this button, I will get character 2 in ASCII transmitted to the UART to TTL converter, USB to TTL converter connected to the PC. So double click on this COM and select the respective device. Just click on the drop down. You can see one USB serial port device, that is the USB to TTL converter, has been connected to PC that we already connected, and click on OK. Baud rate is 9600, no change in that. Now I'm just going to start the communication by clicking on the start button right over here. Now when I press on this button, you can see the character 1 is transmitted, and in the RX data variable, I am receiving the character 1 in ASCII. And when I click on this button, and you can see the LED on the development board is lighted up. So as per our expectation, when the character data is 1, our expectation is the LED must be turned on. That is, the LED connected to 6-7 pin of the port must be turned on. And when I press on the button 2 for transmitting the character ASCII 2, you can see the RX data variable is having the value 2 and the LED is turned off in the development board. And when I click on 1 again, or when I transmit the ASCII 1 again, the LED is turned on in the development board and the RS data variable is having the value ASCII 1. Again, when I transmit 2, you can see the successful transmission from docklight has happened from docklight to the microcontroller variable RX data, and the LED is turned off. So 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2, 1, 2. So this is how you can receive a byte of data using UART serial communication in RL78 bar F14 series microcontroller. So as per our expectation, the interrupt is also happening. We are only receiving the data inside the interrupt receive function right over here. That is the interrupt subroutine function required for receiving the UART data. So this is that function. We very well know that UART0 interrupt receive is the interrupt subroutine function or interrupt service routine function, which is useful for identifying the UART reception in the microcontroller. So inside this we have written this line, that is the RX data is equal to RX data. We are reading this variable which will be holding the data that has been received from the UART terminal. So once a successful reception happens in the UART port of the microcontroller, this interrupt subroutine function will be called, and inside this many things are happening. But only thing that we are doing is we are just manually loading the data that we get inside this RX data variable as local variable to this function to the global variable that we have defined and declared in our user program, that is the RX underscore data variable. So let me just keep a breakpoint right over here, and when I run this, and I'm just opening the docklight for manually seeing whether how it is working. So the expectation is whenever I transmit a byte of data from any other serial terminal to the microcontroller serial port, this interrupt subroutine function will be called after successful reception of a byte of data. So when I click on this, you can see the breakpoint has been hit right over here, which means this function is called, that is the UART reception interrupt is called. So this breakpoint inside the interrupt subroutine function for reception of data in UART has been hit. I'm playing this. Again, when I transmit this, you can see again the breakpoint is hit, and in the respective RX data variable I'm having the data 1, and once after executing this, the current data will be loaded to this RX data. This is how this RX data variable is being updated inside the interrupt subroutine function. That's it. So this is how we are using the UART serial interrupt for properly receiving the byte of data. If you want to receive a consecutive bytes of data or set of bytes of data, you can use a buffer right over here, and you can increment the buffer element variable for continuously receiving a certain bytes of data inside this interrupt subroutine function. The method is same, but the only thing is you just want to alter the logical part a little bit for receiving a continuous set of data. That's it. So I hope you learned the basic techniques for receiving a byte of data using UART communication in RL78 bar F14 series microcontroller in this video. See you in the next video. Thanks for watching.